So we all know that double sideband suppressed carrier is just the product of the modulating signal and the carrier signal. And we all know that the modulating signal is given by the expression Em cos omega mt, and so this can also be written as Em cos 2 pi fmt. Similarly, the carrier wave can be written as Ec cos omega ct or Ec cos 2 pi fct. Right? So now we have the double sideband suppressed carrier, the expression for DSB-SC. So now what I am trying to do is, we have, if you remember, we have done a similar analysis in AM, double sideband full carrier, wherein we have got the three components: the carrier component, the upper sideband component, and lower sideband component. And for each component, we have the corresponding amplitude values. And we have calculated the power of each component by taking the RMS value of the amplitude, right? Power is equal to the square of the RMS value of its maximum amplitude. So same, based on the same concept, we are now trying to get the expression for power. So here, for double sideband suppressed carrier, we have x of t, which is Em cos 2 pi fmt into Ec cos 2 pi fct. So taking Em and Ec out, so we have cos A, cos B. So this will become 1 by 2 into cos of A plus B plus cos of A minus B. So 2 pi t is common. I am taking that as common, right? Cos of A plus B plus cos of A minus B. So expanding those braces, we'll be having, so this Fc plus Fm is related to the upper sideband frequency, and Fc minus Fm is related to the lower sideband. And we know that in double sideband suppressed carrier, we have only the two sidebands. The carrier is suppressed. So now expanding the braces, we will get S of t is equal to Em Ec by 2 multiplied by cos 2 pi into Fc plus Fm into t plus Em Ec by 2 cos 2 pi into Fc minus Fm into t. And these are the two sidebands. So this is the expression for double sideband suppressed carrier, wherein only the two sidebands are present. So this is the one sideband, this is another sideband. So this Fc plus Fm corresponds to the upper sideband, and this is the lower sideband. So the frequency of upper sideband is Fc plus Fm, and its amplitude is Em Ec by 2. So this is the amplitude of the one sideband. Similarly, for the other sideband, the amplitude is Em Ec by 2. So both the sidebands will have the same amplitude, and the frequency is Fc minus Fm for lower sideband. So now to calculate the power, we have to take the RMS value. And we know that P equal to V square by R, right? If you remember, we have taken P equal to V into I. And as per Ohm's law, I equal to V by R. So where R is the resistance, right? So now here we have only the amplitude values. We are taking the equation, the expression for power in terms of voltage. So now the power of the sidebands can be calculated as, so, and this V square is the square of the root mean square value, and root mean square value is the maximum amplitude divided by root 2. So the RMS value of amplitude will become, so I am now writing the expression for power of upper sideband, which is equal to power of lower sideband, which is equal to 1 by R multiplied by V square. So that is the RMS value. That is the RMS value. EM EC by 2 root 2 whole square. Correct? The square of the RMS value divided by R. So this will become EM square EC square by 2 square is 4, root 2 square is 2. So 4 2s 8. So this will become 8R. So EM square EC square by 8R is the power of the sidebands. Is that clear? So in order to get the total power, so the total power in the case of double sideband suppressed carrier, so this will be equal to PUSB plus PLSB. In the case of conventional AM or the double sideband full carrier, we have got DC plus PUSB plus PLSB. So there we have 3 components. One is the carrier component along with the 2 sideband components. So, but here in this case of double sideband suppressed carrier, the carrier component is completely suppressed. So we'll be having only the 2 sidebands. So the total power will become, so both are equal, right? EM square EC square divided by 8R plus EM square EC square by 8R. So the total power will become EM square EC square by 4R. So the total power for double sideband suppressed carrier is EM square EC square by 4R. So where EM is the amplitude of the modulating signal and EC is the amplitude of the carrier signal. So next we will see a problem. So look at the question. I'll share the question bank with you once again. So if you see the question related to the second unit, yeah, this one. So we'll solve this. So, and here's the question. Just go through it once. Illustrate the effect of phase error on the output of coherent detector. So here we have to simply take the coherent detection of double sideband suppressed carrier and followed by a problem is there. Calculate the percentage of power saving. So we have to show that the power is saved when 100% modulation is done and 50% modulation is done. So in the case of AM, double sideband full carrier, so by using the expression for total power, which is equal to PT equal to PC into 1 plus M square by 2. And for 100% modulation, we have taken M equal to 1. And there we have seen that PT equal to 1.5 PC. And we came to a conclusion that around 67% of the total power is wasted by the carrier. But in this case, we are suppressing that carrier, which means that 67% of power which is wasted in the earlier case is now saved. So that's what we are going to prove in this problem. Please stop me if in case of any doubts. I hope you are all following the pace with which I am going. Let me know if there is any difficulty in the chat box. Right. So in order to calculate the phase error, so here the given one is the coherent detection. And we have to show the output of coherent detection and the effect of phase error on the output of coherent detection. We have already seen this. We have got the phase difference phi. So because of that, we have got the extra term cos phi. So for DSB-SC demodulation, we have a product modulator. So for which the input will be given as double sideband suppressed carrier. So let us assume this as S of t, which is given as x of t cos omega ct. And the locally generated carrier. So the other class, I think one of you have asked me about the difference between coherent wave and a non-coherent wave. So here at the output of product modulator, depending on the phase error that is coming up from the local oscillator. So this is basically a local carrier oscillator, which we are assuming as cos omega ct plus phi. Right? If this phi is equal to 0, then we can say that. So that phi equal to 0 implies the phase difference is 0. If the phase difference is 0, then this signal from the local oscillator will be in synchronization or will be in coherence with this wave. So phase error 0, the output can be reconstructed accurately. So when this is passed through the low pass filter, because there is no error, we can get back our exact message signal. If there is a certain phase difference phi, so the message signal is scaled by a certain factor. So we don't get the exact message signal, but its amplitude is little varied. So we have to reconstruct the approximated version of the signal. So that's the difference. A coherent wave and non-coherent wave means in the case of coherent wave, phi is equal to 0. Non-coherent wave means phi will be having a certain value. Right? So that's the difference. I hope this clarifies. So now we'll calculate the output of coherent detector. So let us assume the output of product modulator as V of t and the output of low pass filter as V naught of t. So now we have V of t is the product of these two, S of t and C dash of t. And we know that S of t is x of t cos omega ct multiplied by cos omega ct plus phi. In other terms, we can also write this as 2 pi fct. So we'll write that here itself. X of t cos 2 pi fct multiplied by cos 2 pi fct plus phi. Same analysis we have done. So only thing is that we are asked to illustrate the effect of phase error. So in order to prove that, we have to do all these things. And this is in the format of cos A, cos B. So we'll take EC also here. So EC cos omega CT plus pi. So here also you'll get EC. So the V of t expression will become 1 by 2 EC x of t multiplied by cos A cos B, right? Cos of A plus B. So that will become cos of 4 pi FCT plus pi plus cos of A minus B. Correct? 1 by 2 into cos of A plus B plus cos of A minus B. And this term, out of these two terms, the first term, these are the terms which are passed through the low pass filter. And when passed through the low pass filter, only the low frequency components are passed and these higher frequencies are eliminated. So the output we will get as V naught of t will be equal to 1 by 2 EC x of t cos phi. Right, now we have to calculate the effect of phase error. So the effect of phase error. So we'll consider the maximum and minimum values of the phase value. So for phi equal to 0, the output of the coherent detector will be maximum. The output of the coherent detector will be maximum. So that is V naught of t equal to 1 by 2 EC x of t. So where this is the scaling factor. Similarly, for phi equal to 90 degrees, then the output of the coherent detector will be 0. So that is V naught of t is equal to 0. Cos 90 is 0, and this is what we are calling as quadrature null effect, right? So this is the effect of phase error on the output of the coherent detector. So we have considered the maximum and minimum values. So this is what you can write when this question is asked. Right? This is the effect of phase error on the output of coherent detector. So now we'll go with the second half of this question. So we are asked to calculate the percentage of power saving for a double sideband suppressed carrier signal for the percentage modulation 100% and 50%. So percentage of power saving we have to calculate. So in order to calculate that, we have to consider for m equal to 1 and m equal to 0.5. 100% and 50% are given, right? So in order to calculate that, we have to get the total power of AM. So we have to compare this with AM. Only in that case we can get back. We can understand how much of the power is saved. So the total power of AM wave is given by PT equal to PC into 1 plus M square by 2. So don't get confused, even if we have considered mu. So both are same. M and mu represents the value for modulation index. And we have seen that at 100% modulation, the value for M is equal to 1. Then the total power will become 1.5 PC. Right? 1 plus 1 by 2. And from this, we have to calculate the percentage of power saving. So there we have told that from this equation, we came to a conclusion that around 67% is wasted by the carrier because it is taken by the carrier out of the total power. So now this carrier is suppressed. So now we'll see percentage of power saving will be equal to the carrier power divided by the total power. So that will be equal to PC divided by 1.5 PC. So we'll get 1 by 1.5. So how much you will get? 1 divided by 1.5. We take the calculator. Type in the chat box if you have a calculator. So we'll get around 66.66%. So that is the percentage of power saving. Similarly, for at 50% modulation, the value for M is equal to 0.5. Then PT will become PC into 1 plus 0.5 whole square divided by 2. So 0.5 whole square is 0.25 divided by 2. Calculate and tell me how much value we'll get for total power in terms of PC. Type in the chat box if you have got the value. This we will get 0.125. So the total power will become 1.125 PC. And same thing, percentage of power saving will be equal to the carrier power divided by the total power. Carrier power is PC, total power is 1.125 PC. So that will be 1 divided by 1.125. Tell me the value for this. Type in the chat box, please. How much percentage we will get? 1 divided by 1.125. Yes, 88%. Telling that. G8. G8 have responded correctly. Good job. So it is 88.88%. So at 50% modulation, the percentage of power saving is 88.88%. So that's about the problem. Left with 10 more minutes. So quickly we'll go to the other problem. So we'll solve this problem.